Have you ever wondered where the stars in our night sky come from? This question has fascinated mankind for millennia. The answer resides in the vast, boundless cosmos, in a place where stardust comes to life, the nebulae. Nebulae are the celestial nurseries of the universe, where stars are born and begin their cosmic journey. They are vast clouds of gas, dust, and other matter, suspended in the infinite expanse of space. Imagine a cloud on a lazy summer day, but instead of being made of water vapor, it's composed of hydrogen and helium, the very building blocks of the universe. Existing in a variety of sizes and shapes, nebulae are scattered across the cosmos like cosmic confetti. Some are merely a few light years across, while others span hundreds of light years. Their forms are as diverse as their sizes. Some nebulae are round and fluffy like cotton candy, while others are twisted and intricate like the patterns of a kaleidoscope. These nebulae are not just composed of gas and dust, but also contain other matter. This matter includes everything from particles left over from the creation of the universe to the remnants of dead stars. Imagine a celestial recycling program where the old gives way to the new, and the cycle of life continues on a cosmic scale. The composition of nebulae is crucial to the birth of stars. The gas, primarily hydrogen and helium, provides the raw material that will eventually ignite and form a star. The dust, on the other hand, serves a dual purpose. It not only provides the seeds around which a star can begin to form, but also shields the nascent star from the harsh radiation of space, allowing it to grow and mature. So next time when you look up at the night sky, remember that each twinkling star you see began its journey in the heart of a nebula. These nebulae, with their gas, dust, and other matter, are the cradles of the cosmos. So the journey of a star begins in these cosmic nurseries called nebulae. So, how does this vast cloud of gas and dust turn into a star, you may ask? Well, let's dive into the fascinating process where the magic of the cosmos happens. It all starts with gravity, a fundamental force that governs everything in the universe, from the tiniest particles to the most enormous galaxies. In the heart of the nebula, gravity plays a crucial role. You see, the nebula is not a uniform cloud. It has regions denser than others. And it's in these denser areas where gravity pulls the gas and dust particles together, causing them to contract. Now, imagine squeezing a sponge. The more you squeeze, the denser it becomes. The same principle applies to these contracting areas within the nebula. The particles become denser and denser, compacting closer and closer together, and as they contract, they also heat up, a reaction resulting from the increased pressure and friction among particles. This contraction process continues, and the region becomes denser and hotter, forming a hot, dense core. And voila, we have a protostar, the earliest stage of a star, but don't get fooled by its name. Although proto means first, this is not a star just yet. It's more like a star in the making, a stellar embryo if you will. This protostar is still enveloped within the nebula, invisible to the naked eye. But within its core, the temperature continues to rise, and the pressure continues to build. However, it's not quite hot or dense enough for nuclear fusion to occur. That's a story for the next stage. But for now, let's take a moment to marvel at this extraordinary process. From a vast, cold cloud of gas and dust, gravity has sculpted a hot, dense core. A core that, given enough time and just the right conditions, will eventually ignite into a brilliant star. And just like that, from the nebula's contraction, a protostar is born. What transforms this protostar into a full-fledged star, you might ask? Well, the answer lies in the heart of the star itself, where the temperature and pressure continue to rise, setting the stage for a process known as nuclear fusion. As the protostar matures, the pressure and temperature at its core reach staggering levels. We're not talking about the kind of warmth you feel on a sunny summer day, or the pressure you feel when you dive deep into the ocean. No, we're talking about temperatures of millions of degrees and pressures billions of times greater than what we experience here on Earth. Under these extreme conditions, something extraordinary happens. The hydrogen atoms that make up the majority of the protostar's mass start to come together. They move at such high speeds that they overcome their natural repulsion for each other. In a process akin to a high-speed dance, 4 hydrogen atoms combine to form a helium atom. But here's the kicker. The helium atom is slightly lighter than the 4 hydrogen atoms that made it. So where did the extra mass go? It wasn't lost, it was transformed into energy, as dictated by Einstein's famous equation E=mc2. This energy, in the form of light and heat, radiates outwards, providing the pressure needed to counterbalance the immense gravity pulling everything inwards. This is the process of nuclear fusion, the powerhouse of a star. It's like a cosmic-scale pressure cooker, where the heat and pressure cook up hydrogen to create helium, and in the process, release a tremendous amount of energy. This energy is so vast that it can power a star for billions of years. It's this very process that illuminates our night sky, that powers our sun, and that makes life on our planet possible. It's this process that transforms a simple cloud of gas and dust into a dazzling beacon of light in the cosmos. This delicate balance between gravity and outward pressure gives birth to a star. And just like that, a star is born, a testament to the marvels of the universe and the immense power of nuclear fusion. So, what happens after a star is born? Well, once a star is born, it enters a phase of life known as the main sequence. This is the longest period in a star's life, where it exists in a stable state. It's comparable to how we humans spend most of our lives as adults doing our day-to-day jobs. For a star, that job is to fuse hydrogen into helium. This nuclear fusion process releases a tremendous amount of energy, which we observe as the star's light and heat. Now you might be wondering, how long does this main sequence phase last? The answer lies in the star's initial mass. Larger stars have more hydrogen to burn through, but they also burn it at a faster rate. So paradoxically, the bigger the star, the shorter its lifespan. A star like our Sun, which is of average size, will spend about 10 billion years in the main sequence. But a supermassive star, it might only last a few million years. The star's mass also determines its color and size during the main sequence. Smaller stars with less pressure and heat at their cores glow a cool red. On the other hand, massive stars with their intensely hot cores shine a brilliant blue. In terms of size, the star's mass dictates how much gravity it has, which in turn determines how big the star can get before the gravity pulls it back into a spherical shape. So, a star spends most of its life in this main sequence stage, continuously fusing hydrogen into helium, shining brightly, and providing light and heat to any surrounding planets. It's an intricate balance of gravitational pull and outward pressure from fusion, a delicate dance that can last billions of years. But all good things must come to an end, and so it is with a star's life in the main sequence. When the hydrogen fuel begins to run out, the star enters the next stage of its life. But that's a story for another time. And that's how a star lives, shines, and gives light to the universe. So, how can we summarize this mesmerizing process? Well, it all begins in the vast quiet spaces of the universe, where cosmic clouds of dust and gas, known as nebulae, float aimlessly. These nebulae are the birthplaces of stars, where stellar nurseries are formed. The nebulae are made up of hydrogen and helium, with a sprinkle of heavier elements. These clouds are so vast that they can span light years across. Now, within these nebulae, certain pockets begin to contract under their own gravity. As the particles within these pockets draw closer together, they form a spinning disk of material with a concentrated center. This central concentration is what we call a protostar. It's essentially a baby star, a cosmic toddler, if you will, taking its first steps in the universe. As the protostar continues to draw material from its surrounding disk, it grows in mass, and consequently, its core temperature rises. Eventually, the core temperature reaches a critical point, igniting the process of nuclear fusion. This is where the magic happens. Hydrogen atoms in the core start to fuse together to form helium, releasing a tremendous amount of energy in the form of light and heat. This is the moment our protostar graduates to stardom, literally. It's now a fully fledged star, shining brightly in the cosmos. The star then settles into its main sequence stage, the longest phase of its life. For billions of years, it maintains a delicate balance between the inward pull of gravity and the outward push of pressure from nuclear fusion. This is the stage where our sun currently resides, steadily fusing hydrogen into helium, radiating energy, and making life possible on Earth. And that's the extraordinary journey of a star, from a simple cloud of dust and gas to a shining beacon in the cosmos.